Welcome to this video on the twin paradox, explored through the lens of time, or TTT diagrams. We will walk through a step-by-step revisualization of the paradox. We begin with the traditional Minkowski diagram, the foundation for understanding space-time transformations. Next, we rotate the court and court prime axes to reorient our perspective on these space-time coordinates. Moving toward the Epstein diagram, we introduce space-proper time diagrams, or SPT, to further simplify our analysis. This approach allows us to transition from the standard Minkowski framework into the Epstein representation. Continuing our process, we now transposing the x and court prime axes to refine our visual model. We then proceed to displace the x and x prime axes, a critical step in building the TTT diagram structure. By finalizing these geometric shifts, we arrive at the TTT diagram, designed to offer a new perspective on the twin paradox. Here is the completed TTT diagram, showing the final alignment of the transformed axes. In this final configuration, the TTT diagram clearly illustrates the relationships between the original and transformed spacetime. Now, let's examine the notation used in the TTT diagram to represent the various time and space components. This slide displays the trigonometric relationships inherent in the TTT diagram, relating velocity and the Lorentz factor. This diagram summarizes the designation of the time variables, highlighting how they interact within the geometry. Finally, with a velocity of 0.1 c, we can observe the calculated values for our trigonometric variables in this model. We begin our exploration of the basic diagram with a look at how time is represented on the horizontal axes. Representing time on the horizontal axis offers distinct advantages, such as providing a more flexible vertical axis. Furthermore, this model allows the observer to remain at rest in space, while their position in spacetime remains dynamic. Moving to the next view, we focus on the relationship between coordinate time and spatial distance, labeled as court by s. This diagram explicitly maps the relationship between proper distance and coordinate distance through the variable phi. Here we visualize the vector path, showing how proper distance, s, is defined by the velocity ratio relative to light speed. The formula s equals v times t is derived here as the product of the velocity ratio and coordinate time. The transformation for proper time, t prime, is explicitly shown as the product of the Lorentz factor and coordinate time. This slide breaks down the specific definitions for time in years and space in light years within our system. We now define the variables t and delta, providing clear labels for our time and coordinate measurements. Finally, we introduce the lambda factor to simplify the transformations applied to the coordinates throughout our analysis. The diagram displays the vectors for approach and departure, providing a visual representation of the traveler's movement. To conclude, this diagram marks the synchronization phase, vital for ensuring accuracy when measuring time across different frames. We continue by examining the geometric representation of these movements between points A and B, maintaining our focus on the TTT diagram structure. This visualization deepens our understanding of how the synchronization vectors interact as they cross the established spacetime trajectory. We now break down the coordinate versus proper time variables, showing their distinct roles in the twin paradox calculation. To wrap up, this final diagram maps the complete timeline, providing a clear overview of the relativistic time dilation experienced by both participants.